The pattern? Okay. Am I gonna fill it up?
Yeah.
Wash it further. All right. So yeah. Now, like I said last time, if possible, we'll try to make these kind of experience fun. And I didn't have to do that for college algebra because the math is not really that bad, right? I mean, math is not bad, but it's just trig. Even though I don't want to say that as an instructor, but I do remember when I was at your age, learning trig is really nightmare. It's not hard, right? Sometimes you just feel overwhelmed, right? The too many things you have to memorize, right? And you know that we're not good at that. Anyway, so that's a touch screen. All right, so now let me switch back to my laptop and I'll zoom out a little bit to show you. Don't hate me. There will be more identities. And yeah, unfortunately, so almost every day in the next couple weeks, you guys are getting new identities almost every single day, like new formulas. Right. So I guess that now you're not gonna say that, oh, I like formula, I want a cheat sheet. So now guess what? A cheat sheet of 1,000 formulas on that, you're not gonna like it. But I do want you to appreciate the quotient identity, and not to mention the Pythagorean identity. Oops. First off, you see quotient, since I've already showed you before, it's not hard at all. Since you have two of them, but they're related, right? So you just have to remember tangent is sine divided by cosine. And you don't have to memorize the cotangent, since cotangent is the reciprocal of the tangent, right? You just go ahead and flip the numerator denominator and you get the second, quotient identity. Okay? So for Pythagorean identity, it might be a little bit, tricky to memorize all three. That's why my suggestion is you remember the first one, which is the most important one. And I'll show you how to prove it. So that means if you're desperate that you just don't remember this identity, but for sure you need it for a certain quotient, it should be able to just you should be able to prove that to yourself within like a minute. And also I'll provide you some assistance like proving the other two, so you can do that after class. All right. Now, feel free to take notes of how I prove the first Pythagorean identity. Scroll down. All right, so I'm going to draw a right triangle. And this is what I mean by angle theta. Now here's the right angle. So the opposite side, I'm going to use letter O. And the adjacent side of a theta, let's say capital A. Hypotenuse, I'll go with H. All right, so let's recall the famous Pythagorean theorem. Okay, which says that when you add up the square of the two shorter sides of a right triangle, in this case it's the opposite square plus the adjacent square, right? And it's going to be equal to the hypotenuse square. So now I want you to divide out the h square. across the board. All right, let's see what we get. So dividing every single term by h squared. So I have O squared over h squared plus a squared over h squared equals h squared over h squared, right? Now the first term on the left, is it okay if I write it as over h entirely to the second power? You guys remember this is a property of the exponent, right? If you're taking a power of a division, you get the distributive power, so then the numerator and denominator is going to get the same power. You guys remember that back in algebra? All right. Now, the second term, we'll do the same thing. So we'll be looking at a over h squared, right? And obviously, h squared divided by itself, you're going to get 1. And now you guys can remind yourself, what is over h? Opposite of a hypotenuse. Psi. You know, it happens. All right. Yeah. It's psi, right? Psi theta, right? Squared. But is, again, a confusing part. We don't like that since it looks ugly, right? Why am I writing, a pair of parentheses? So they decide to put the square right next to the sign. And everyone knows that this is not just squaring the name of the function. It is actually squaring the whole function. Right? It's sine of theta, but getting squared. You only get to do that with the trig functions, putting the power next to the name of the function. No need for a pair of parentheses. A over h will be cosine, right? And there you go. Now let me zoom out a little bit. Feel free to take a picture. Once you're done, I want you to think for maybe just a minute. If you can think of a way just like that to prove maybe the second identity, and you have to show me the work. You can try that, after class. But I do want you to tell me if you have any thoughts about doing the same thing. But instead of getting sine and cosine square, you want to get tangent square and secant square out of the Pythagorean theorem. All right, go ahead, 1 minute. Think about it. All right, any thoughts? All right, anyone want to share your thoughts? Now I want tangent square, secant square. And you see what I did, and that's pretty much the key thing, right? Is to divide something to recreate sine cosine and also get myself the 1. So I still need a 1, but instead of getting sine and cosine 1, the tangent secant. Yeah, Alex. Okay, we divide everything by a squared. Now, I don't want to write it down, so Because can you imagine if I divide out this guy by a squared, O over a is opposite adjacent, that's tangent, right? Squared. A squared over a squared is 1. That's exactly what I want, right? Now, h over a. H over a. So that's the reciprocal of a over h. A over h is cosine. What's the reciprocal cosine? C. So yeah, that takes me like 5 seconds to process that and figure it out. But that means it's normal if you have to do that. But you know what? If you do that for a couple of times, it's not going to get any quicker because 5 seconds is still short enough, right? But at least that you're not going to get it wrong. So now, of course, you can do the same thing for the third identity, right? So that means don't triple the work, right? When you memorize those identities, just like the ratio identity, it's just one identity and it's reciprocal. Here is, again, one classic version, right? Sine squared plus cosine squared is equal to 1. And for the other two versions, if you need them, you can get them on your own, just by writing down the Pythagorean theorem. And that's how the identity gets its name. So I will say that they are equivalent, but just in different forms. Anyway, all right. I guess that you guys are fine with them now. But trust me, I don't feel good about doing that, but this is there are more identities. All right. But you see that I didn't say that. Remember this, all right? Because they are not that hard to understand and find them, something that it has to happen, for those functions, right? But let me point out the way they name those functions, right? So cofunction. Right, those 6 identities are called cofunction identities. What do I mean by cofunction? The sine and the cosine. See that they name the way so that those two functions are cofunction of each other. And as relative speaking, right? Cosine is the cofunction of the sine. But the other way around, sine is also the cofunction of the cosine. Does it make sense? All right. So now, secant and cosecant are cofunction of each other. Tangent, cotangent are cofunction of each other. Now, what's so special about the cofunctions? If you have a function evaluated at a certain angle, and it turns out that its corresponding cofunction evaluated at the corresponding complementary angle will have the same value. For example, sine 30 is equal to cosine of 60. All right. Check that. 30 plus 60 is 90. That's why they're called complementary angles. So the function at the third angle 30 degree is equal to its cofunction evaluated at its complementary angle. I guess that you might like 30 and 60. Oh, I guess that just be consistent to me, but or get rid of these here. But please understand that the way they put it, like 90 degree minus theta, is just trying to get you the corresponding complementary angle, right? Now, and it turns out that this is, of course, identity. That means it works for general. It doesn't matter, whether the angle is measured in degrees or radians. That means I can write down another identity, say cotangent pi over 3 must be equal to its cofunction, which is tangent, right? So, well, now you guys tell me what will be the complementary angle of pi over 3 in radians. Just remember that 90 degrees is the same thing as pi over 2 radians. That means we're looking at pi over 2 minus pi over 3, right? How much is that? Say it again. Oh, you're thinking about the degree. That's fine, but I want the radians. Yeah, it is 30 degrees. Right. The corresponding radians will be pi over 6. Yeah. So of course, if you carry out the subtraction, right? Just in case. All right, so we're talking about pi over 2 minus pi over 3, right? So you are really just subtracting 1/2 and 1/3, right? Can take the pi out. 1/2 minus 1/3. You know that you're gonna write the 1/2 as 3/6, right? Minus 2/6. Just by finding the common denominator, you get 1/6 pi, right? Or pi over 6. All right. But my point is, you need to open to angles during radians. Okay. Anyway, so once again, these identities will be also pretty handy. But if you don't remember them, that's fine. But I guess that if you're talking about angles in degrees, there's no way you can miss that. Because I'm saying that there's got to be a reason why they call functions the cofunction of each other, right? So somehow they're related, but in this kind of interesting way. All right. Now, let me show you some examples in the book. So now we have quite a few identities, right? Forget about the basic ones. So we talked about quotient, right? Reciprocal identities, right? Quotient identities, and Pythagorean identities, even cofunction identities. Let's take a look at example number 5. All right, so we have the value of a sine and a cosine given, but they wanted to find out all the remaining 4 trig functions. So I hope that by recalling the quotient identity, dividing the sine and cosine, you're going to get tangent right away. Right? But there's some technical details. Say, dividing fractions. You guys do know how to go into multiplication, right? So that's something I'll typically have to make sure you get it right. Over here, they are rationalizing the denominator. Okay. But my question is, the problem didn't say that you have to rationalize the denominator, right? Would it be okay to leave the answer like that? Yes. Don't waste your time in a test. If you get a free response and it doesn't say that you have to rationalize the denominator, then don't do it. All right. Because remember that what's wrong with denominator, which is radical 21? It can be radical, it can be irrational, right? But think about this. A rational number is not a bad number, right? There's nothing wrong with it. Think about what is one of the most important irrational number in your life. Pi. It's irrational, right? If you hate a pi, then I think the world would be very different. Right? So it's not wrong to have a rational denominator. And for some reason, mathematicians don't like that. And they ask you to do one more step to do it. But seriously, there's not going to be any difference between these numbers, except for some cosmetic, things. All right. Now, once you get the tangent, I think that is a way to and I need to learn this, there should be a way to quickly erase everything. All right, so let me scroll down so you can see what they did to get the remaining functions, like secant and cosecant and cotangent. So now please do not spoil yourself. So take every chance to practice the logic behind memorizing the relation between secant and cosine, right? Cosecant and sine, and tangent and cotangent. So just taking reciprocals, right? Now the sine is, as what they told us, pi half. No, pi half, 2/5. Reciprocal is me pi half, right? That's fine. For cosine, you get a nice form in the first phase because it doesn't have a irrational denominator. But once you flip it, you get 5 over radical 21. Like I said, it's fine. Why would you bother to rationalize denominator if you didn't have to? Right? So if you want to do that, you get something like this. For tangent, now this is the part I feel like that things might not be as consistent as you thought in a textbook. They literally plug in the ugly form for the tangent, right? Remember that the tangent was 2 over radical 21, and I said that it's perfectly okay for you to keep it. But they insist that you're going to have to rationalize the denominator. But now you see that they substitute this value into the tangent. That means it's implied that you are allowed to use it, right? But you get my point, right? So if you don't have to rationalize the denominator, forget. But the beauty of a plug-in this form is when you flip it, you get a slightly nicer form. So now would you say that using ratio identity and let's say the reciprocal identity, you'll be surprised at how much you can work out based on even just the values of some sine cosine functions without really drawing a triangle and label the sides, right? And finding those ratios and try to memorize all those different definitions of all 6 functions. And later on, you'll see that it's very rare you're going to draw triangles, right triangles. So you're going to be playing with those values of sine, cosine, and stuff, right? And tend to work out the remaining functions. Not to mention that, 5.3 will introduce the angle beyond 360 degrees. We'll also introduce trig functions beyond the right triangle, right? That means, you're not going to have triangle anyway, so don't get too used to using that. Anyway, so now we've seen the Pythagorean identity, right? And because we have an example here saying that now let's say you're given only the sine theta, right? 3/5. You want to find out the cosine. Right? And what you have to do is hopefully realize sine and cosine are related through the Pythagorean identity, right? So start from writing down that identity that makes a substitution. And then you're just solving for the unknown, which is cosine, right? But since cosine was raised to the second power, so make sure that once you isolate the cosine square, going to be getting the number, and you have to take the square root at the end, right? So let's try one problem just like that to make sure that since after all you're still solving for equations, right? Not to mention it's technically speaking a quadratic equation, right? Even though it's the easier kind, let's make sure that no one's really having an issue with the algebra here. And also I want to show you that you could do even more than just solving for the cosine. You could actually work out all the remaining functions, and there's a little trick to do that without memorizing a whole lot of identities. Right. Anyway, so let me switch back to my laptop. All right, so now this one, if you ask me for the notes or if you're going to be watching the recording, you see that this is the same problem, pretty much the same problem as we talked about in the textbook. All right, so I'll skip that. All right, so let's try this one. All right, so we have the value of the sine given, and we're trying to find the cosine. All right, so we're going to start from the Pythagorean identity. All right, so now we're going to substitute the value for the sine. So you're getting 1/2 squared, right, plus cosine squared. All right, solving for the cosine, but you're going to isolate the cosine square first, right? So you can subtract both sides by 1/2 to the second power. All right, so you're getting cosine square equals to 1 minus, well, square root of 1/2 is 1/4, right? So you're getting radical, well, actually not radical yet, right? 3/4. Don't forget to take a square root. All right, which gives you that, right? Of course, this happen to be, a nice number in a sense that the denominator is a complete square, right? Which you didn't have to rationalize. If you want to do it, then it's automatically done. But like I said, even if you leave the answer like 3/4 on a radical, in the test, if I didn't ask you to rationalize the denominator, you'll be fine. But I'm sure that you can tell from those multiple choice options. If you don't get anything that matches your answer, think about, is it because that you didn't simplify enough, right? Or you didn't rationalize the denominator. All right. So now as you guys finish up the notes or, trying to take a picture, I want you to think about, what if I'm asking to find out all the remaining functions? Say cotangent or secant. Yeah, Mateo? If you want to, yeah, what would you do? Mm-hmm. Exactly, right? It's just like what the example 5 showed us, right? Okay, now a bit further. What if I didn't say find out the cosine first, then work out the remaining? It's a problem in the test. It just asks you to find out all 5 remaining functions based on the fact that sine is 1/2. I mean, you can say, you know what, I'm going to still do the cosine, then use the ratio to find the tangent, then flip all 3, right, to get the remaining 3, right? That, that could be a routine, which is perfectly fine. But let me show you what if I use the right triangle to assist the whole process. And you'll see that it will be a lot faster. I know that I just said try not to get too used to using the right triangle, right? But, just be practical. If you do have a way that's going to get you an answer right away in a test, use it, right? But of course, if possible, do not spoil yourself. Now let me draw a right triangle, and I'm going to label angle theta here. Since they told me sine theta is 1/2, how should I label the sides? Remember, the sine represents opposite over hypotenuse, right? Can I just label the opposite, which is 1? I mean, not necessarily 1 inch, 1 feet, it's 1 unit, right? And our hypotenuse has to be 2. So now what about the missing side? How much do you think the adjacent side has to be? How do you figure out it's 1? Now, remember, it's not the sides add up, their squares add up due to the, Pythagorean theorem, right? That means you're actually going to get, for the third side, the missing side, it's the square root of hypotenuse square minus one of the shorter side square, right? This is actually radical 3. Okay. Now, it happened to be a special triangle, right? But you don't have to know that. All right, so now let me go ahead and write down all 6 functions. Sine theta, cosine theta, tangent theta. Now this is, what is that? Cosecant, secant, and a cotangent. Right? Can you guys read off those functions for me? Sine is what? What? Opposite over hypotenuse, 1/2. Cosine, adjacent to the hypotenuse, radical 3 over 2. Right? Tangent, opposite of adjacent, 1 over radical 3. Right? Now, cosecant, well, that gets easier. Just like Mateo said, you can flip all 3 to get the remaining 3, right? It will be 2 over radical 3, and radical 3, right? Do you guys all see that? Now, how do you like that method? So, I mean, technically speaking, you do have to memorize something, right? How these guys are defined when it comes to the ratio of the sides, and also how these guys are paired. But that's all, right? Not to mention, later on, you see that even if the angle is not acute angle anymore, it can go beyond 90, it can go negative, and the method's going to go work out. But there will be some little adjustments you have to make. All right. But just give you an option, but like I said, going from the ratio identity to get the tangent, right? Well, find out the cosine using the Pythagorean identity, then using the ratio to find the tangent, flipping them using reciprocal identities is perfectly fine. But I prefer that you have a triangle there just to make sure that you don't mess up anything. All right. Well, we do have a couple more minutes. I think that we can achieve a little bit more than that. Do you guys remember the cofunction identities? The 2 functions are cofunction each other. So when you evaluate a function at an angle, its cofunction evaluated at its complementary angle is the same. I'll give you 2 minutes to work out letter A and B. I want you to find out not the value of those functions. I want to know which function at what angle will be equal to sine 46. Not to mention letter B is a bit tricky, right? A function at a certain angle will be equal to cotangent pi over 12 radians. Guys, cofunction is as straightforward as it seems. Cofunction, cosine, cosecant, cotangent. That's why I don't think you seriously have to memorize this identity because it just makes sense. Right? I mean, finally, right after all those many identities, there's something that somehow make a little bit more sense. All right, since it's almost the time, so let me just quickly get you the answer. Feel free to convince yourself. The first one, I think that most people should be, well, all of it should be fine, right? So the cofunction of sine is cosine, and it needs to be 90 degree minus whatever the angle you started with, right, to get to the complementary angle. So that's cosine 44 degree, right? So letter B is only complicated in the sense that you're having the radians. So the cofunction of cotangent is, well, turns out tangent, right? But instead of using 90 degree, I have to use pi over 2, right? Subtracting pi over 12. I'm sure that you'd be fine with, simple algebra involving fractions, right? And it turns out that it is tangent by pi over 12. All right, that's it.